So, Co-17A, today is Happy Halloween. Sorry, let me grab my stuff here. That's not what I'm looking for. There we go. Also, if you have specific questions, you're always more than welcome to ask them. Let's start here. So let's say that we want to take the derivative of f of x equal to x to the fifth plus 1 cubed. Pretending like we don't have the chain rule for a minute. Because we don't yet. We haven't talked about this in this class. So if you don't have the chain rule, what we're going to do, we're going to multiply it out first. So we're going to expand this. This is a great time to use that Pascal's triangle trick again, where if you have something cubed, or I should say something plus something cubed, it's the first thing cubed plus 3 times the first thing squared times the second thing, plus 3 times the first thing times the second thing squared, plus 1 times the second thing cubed. I'm just using that third row of Pascal's triangle, where x plus h cubed is x cubed plus 3x squared h plus 3x squared plus h cubed. Then we're going to simplify this. This is x to the 15th plus 3x to the 10th plus 3x to the 5th plus 1. And now we're going to take the derivative. So we're going to say that the derivative f prime of x is equal to 15x to the 4th plus 30x to the 9th plus 15x to the 4th. And do a little bit more work to see this in a helpful way. So what am I going to do? I'm going to factor out, oh, that's I said 14, I wrote 4th. Sorry there, that's a 14, not a 4. Or should be a 14, not a 4. I'm going to factor out an x to the 4th, and I'm going to factor out, sure, I guess a 15. So if I factor out a 15 x to the 4th, I'm left with an x to the 10th plus a 2x to the 5th plus 1. I'm going to do 2 more things. I'm going to rewrite this 15x to the 4th in a very suggestive way. I'm going to rewrite this as a 3 in front and a 5 times x to the 4th in the back. 3 times 5x to the 4th is still 15x to the 4th. And then in the middle here, instead of writing x to the 10th plus 2x to the 5th plus 1, I'm going to write that as x to the 5th plus 1 squared, which it is. But if you square that out, you exactly get x to the 5th squared plus 2 times x to the 5th times 1 plus 1 squared, which is that. Cool. Another way of doing this, using the chain rule, would have been to have said, great, if my function is f of x equal to, listen to the words I'm going to say for a second. If my function is some stuff to the 3rd power, I like to use the word stuff a lot here. My derivative, well, I know the derivative of x cubed is 3 times x squared. So the derivative of some stuff cubed is going to be 3 times that stuff squared times the derivative of the inside stuff. So the inside stuff is x to the 5th plus 1, and the derivative is 5x to the 4th. And look, those answers are exactly the same. So whether you can, if you can multiply it all out and take the derivative, or if you don't want to, you should end up with the same answer either way. And this is the general idea of the chain rule, is that if you have a function of some inside stuff, you take the derivative of the outside function, you leave the insides alone, and then after that, you multiply by the derivative of the inside stuff. So there's a way to write this down. I don't think it's particularly necessary to know the rule verbatim. Maybe, I don't know. But so the chain rule says, and there's a couple different ways of writing this. One way of writing it is if you're taking the derivative of f of g of x, it's equal to the derivative of the outside function. We'll leave the inside stuff alone. Multiply then after that by the derivative of the inside stuff. Anything else I want to say about this really before I start doing more of this? Yeah. And there's a way to derive this rule. It's not that important though. I mean, like, so you can do this whole thing where you take like f of x to the nth power and then use the product rule n times and get n times f of x to the n minus 1 times the derivative of the inside. So we can point out that there is a quote unquote power rule version of the chain rule, which just says that the derivative of some function to the nth power, well, I'm really just going to use the chain rule and say, I have, bless you, something raised to the nth power. I know that x to the n has a derivative that is n times x to the n minus 1. So in the same sort of way, if I have some stuff to the nth power, the derivative is n times that stuff to the n minus 1. And since I've said the word stuff, what do I have to multiply by? Yeah, here it's, I see you guys mouthing it. Say it out loud. The derivative of the stuff. That's always going to be the answer. If I said we did something with some stuff and then we took the derivative and then we're going to multiply by it, it's always going to be the derivative of the stuff every time if we're doing the chain. So we're going to multiply by f prime of x. And that's kind of really, I mean, we're going to do a lot of examples with this, but that's the whole gist of the chain rule, is that you've got some function that's more complicated where your argument is more than just x. And then at the end of the process, you're going to multiply by the derivative of that argument. So come on in, we're just talking about the chain rule. You can grab one of those handouts, but we're not really doing those handouts, but whatever. We just talked about how if you take the derivative of f of g of x, it's going to be the derivative of the outside function. You leave the inside stuff alone, and then you multiply by the derivative of the inside stuff. So let's do some more examples. Let's say we want to find the derivative of x squared plus 3x to the 10th power. And I want to point out that one reason we use the chain rule is because even though technically you could multiply this out, it would be heinous, right? You don't want to multiply this out and get 11 terms out of the other stuff. Awful. So instead we're just say, great, we have some stuff raised to the 10th power. I know the, and so what I'm really thinking of in the back of my mind is the basic version of this derivative. I know that x to the 10th has a derivative that is 10x to the 9th. I know that some stuff to the 10th has a derivative that is 10 times that stuff to the 9th. But then I said the magic word stuff, so I better multiply by what? Right, which in this case is 2x plus 3. And you better have parentheses around it. Because if you don't have parentheses around it, it's going to look like it's 10 times x squared plus 3x to the 9th times 2x, and then you're adding 3 after you've done the multiplication. So whatever the derivative of your stuff is, if it's more than just one term, the derivative of your stuff better have parentheses around it. Why don't you all try doing this next one on your own? The derivative of x to the 4th plus sine of x to the 12th power. So we've got something to the 12th power. The derivative is going to be 12 times that something to the 1 less power. And then we're going to multiply by the derivative of the inside something, which in this case is going to be 4x cubed plus cosine of x. That's all there is. And you shouldn't bother trying to simplify. By simplifying this is a non-starter, right? You don't want to try and multiply this out. And in general, I would say that's a good rule of thumb on an exam, especially for this first one where you're taking derivative, this first time you're taking derivatives on an exam. Unless it specifically says to simplify, it'll usually say explicitly not to simplify. So don't spend time simplifying unless there's a reason to, or the instructions say to. That's a reason to. Let's look at a couple more. So yeah, let's look at this one. So we want to find for f of x equal to the cube root of x to the 4th plus e to the x plus tangent of x. Sorry. We want to find f prime of x. And before we do that, well, I'm kind of two opinions here. You don't have to absolutely rewrite it, but you should at least think about it as f of x equal to x to the fourth plus e to the x plus tangent of x raised to the 1/3 power. I don't think you need to rewrite it to see that that's what you have, but it's not bad to rewrite it. Then if that's our function, we're going to take the derivative of some stuff raised to the 1/3 power by doing 1/3 times all that stuff. We're leaving the inside stuff alone. Raising it to the 1/3 minus 1 is the negative 2/3 power. And then we have to multiply by the derivative of the inside stuff, which is 4x cubed plus e to the x plus secant squared of x. We're talking about the chain rule. So we take the derivative of the outside function, you leave the inside function alone, and then after that, you multiply by the derivative of the inside function. And while it certainly works for functions where you have some stuff to a power, it actually works for any type of composition of functions. So for example, if you're going to take the derivative of, say, cosine of x cubed plus e to the x plus, I don't know, cotangent of x. We learned last time that the derivative of cosine of x is negative sine of x. Just a quick moment aside here. I think it's really important to say the of x part. I try to say it all the time, so you really shouldn't say just cosine. It's really important to say that you have cosine of something. I'm thinking of the derivative of cosine of x being equal to negative sine of x, so that when I talk about the derivative of cosine of some stuff, it's going to be equal to negative sine of that stuff multiplied by the derivative of that inside stuff. That's going to be a 3x squared plus e to the x minus cosecant squared of x. Let's talk about this just for a minute. So we're not going to prove the chain rule, but I do like to offer you just a little bit more evidence other than that first example that it's true. So we saw that for that first example, which I was a minute ago, where we did, the derivative of x to the fifth plus 1 cubed, we did it two ways. We multiplied it out and took the derivative, and then we used the chain rule, and we saw they were the same. We're going to do one more example like that, just giving you a little bit more reason to believe that the chain rule is actually true. Let's find for f of x equal to sine of 2x. We're going to find the derivative graphically, and then we'll actually say what it is. So, and I know we kind of did this for sine of x, I think last time. So let's look at sine of 2x. I'll point out that sine of 2x has a period of length 1 pi. So sine of 2x looks a bit like this. So it goes from 0 to pi, still has a amplitude of 1. And let's use the color blue. So we're going to cut it into 4 equal quarters. Sine starts at the origin and then moves up to 1, and then moves back down to the middle, down to -1, and then back up to the middle. My sine of 2x function looks like this. And just for comparison's sake, here's good old regular sine of x. Regular sine of x looks like this. Might have gone a little too far there. Oh, well, such is life. Here's regular sine of x. Yeah, I mean, drawn, not the best I've ever drawn it. Okay, here's what I really want to point out with regular sine versus sine of 2x. At the origin, the slope of the tangent line of regular sine is a slope of +1. And for sine of 2x, it certainly looks like the slope of the tangent line would be steeper than that. So what I want to point out is that at this first point here, the slope of the tangent line is more than 1. I will tell you definitively it is equal to 2. So if I start trying to graph the derivative, I know that right here at the beginning, my slope is going to be +2. And then at the next point here, pi over 4, the slope is going to be 0. The next point here at pi, the slope is going to be -2. The next point here at 3 pi over 4, the slope is going to be 0. And back here at pi, the slope is going to be +2 again. So it kind of looks like I took my cosine function and stretched it out vertically. Or in other words, I increased the amplitude by a factor of 2. So it looks like this graph here, which is the graph of the derivative, isn't just cosine of 2x, which has a period of pi, but 2 times cosine of 2x, which totally tracks with using the chain rule. Because if you just looked at your function being sine of 2x, you could say, oh, well, the derivative of sine of x is cosine of x. So the derivative of sine of some stuff is cosine of that stuff multiplied by the derivative of the stuff, which is 2, which is the same as that. So there's a little bit more evidence that, oh yeah, the chain rule really does work the way we think it should work. Yeah, a few more complicated examples, and then we'll move a lot. We'll keep talking. I mean, so I should say we're going to talk. Everything is chain rule from now on. Like, there's like a regular version of a derivative, like for a power of x, or a trig function of x, or an e to the x, and eventually a natural log of x. And then there's the regular, and then there's a chain rule version, which is just you think about saying instead of x, you have some stuff, and then at the end of the day, you multiply by the derivative of the stuff after you've applied whatever rule applies. So yeah, let's look at a couple more examples and then we will make it more complicated. So trig functions work. We've already seen how they work, kind of like you just, instead of doing sine of x, you do sine of whatever, and then take the derivative, you get cosine of whatever, and then you multiply by the derivative of whatever. It's also true for e to the x. And we know that the derivative of e to the x is e to the x. So the derivative of something like e to the x cubed plus 2x plus 9. All right. Well, we know that the derivative of e to the x is e to the x. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. End of story. Let's say 2 more examples like this, and then we'll talk about a nice way of doing this. So what if I wanted to find the derivative of f of x, where f of x was equal to, yeah, let's do this easier one first, and we'll do a harder one. Cosine cubed of x. This one, and so I haven't said these words yet, but when I'm looking at this, I'm always trying to look at kind of the outer function, if you will. I know it's not like, especially the previous example also isn't great for that. When you see e to the stuff, like the e to the is the outer function. It's kind of one of the few functions we have that doesn't look like you don't say e of x, you say e to the x. It'd be nice if it also had that of word in there, but it's just not the way it's said. In the same sort of way, so when you say it that way, it's less obvious what the outer function is. But if you think about it, the inside function is x cubed plus 2x plus 9, and then after that, you're doing e to the whatever that is. In a similar way, it's not super straightforward with this abbreviated notation to tell which function is the inside function and which function is the outside function. So when you have especially a power of a trig function, I highly recommend rewriting it as cosine of x cubed. Because now to me, it's obvious that the inside function is cosine of x and the outside function is raising whatever you have to the third power. So I have something cubed, and I know that the derivative of some stuff cubed is 3 times my stuff squared times the derivative of the inside stuff. And if you felt like writing it less terribly, you can write it as -3 times cosine squared of x times sine of x. So yes, it's a very common abbreviation to, instead of writing cosine of x quantity squared, write it as cosine squared of x. And we kind of go back and forth between them when it's convenient for us. Well, let's look at one more challenging example. Let's say we had something like g of x equal to sine cubed of, yeah, let's do this, e to the x plus 5x to the fourth. Which we should definitely rewrite as sine, I'd pick cube again, how unoriginal, oh well. Sine of e to the x plus 5x to the fourth raised to the power of 3. And here we're going to have to use the chain rule more than once, because the inside stuff that's being raised to the third power is itself a composition of functions where we're going to have to use the chain rule on that piece at the end. So I kind of, in the beginning, kind of like to break these problems up into kind of a two-step process. So, or a multiple-step process, depending on how many compositions we have. So I have some stuff cubed, and then my derivative is going to be 3 times that stuff to the second power, multiplied by the derivative of the inside stuff. And since the derivative of the inside stuff is more complicated than I want to think about at this stage, I'm just going to, sorry, I wanted to brighten that. I'm just going to say, great, I have to multiply by the derivative of sine of e to the x plus 5x to the fourth. But if I write it like that, where I wrote sine of e to the x plus 5x to the fourth prime, it means I then still have to take the derivative in the next step. You don't have to do it like this, and most of the time I won't in the future, where I would just say, okay, and then the derivative sine of some stuff is cosine of that stuff times the derivative of the inside stuff. But it's also totally fine to break it up into multiple steps if that's easier to kind of parse out. So we have 3 times, I'm going to rewrite this as sine squared of e to the x plus 5x to the fourth. I didn't really need the brackets there, but I wrote them. And then the derivative of sine of some new stuff is cosine of that new stuff times the derivative of the new stuff, which is the derivative of e to the x plus 5x to the fourth, which is e to the x plus 20x cubed. And that would be our final gross looking answer. Did I forget a 2? No, it's right there. I moved it. So I just used the abbreviated version of writing sine squared instead of sine of something squared. Yeah. Okay. Let's briefly kind of write down what we have here as far as things we know how to take the derivative of, and then we will move along to talking about implicit differentiation, which is still really the chain rule. I'll point out a lot. Implicit differentiation is just the chain rule, again, thought of in a slightly different way. So here is what we have. Our rules for differentiating. So our function and our derivative. So here are the basic functions we know how to take the derivative of. X to a power, e to the x, sine of x, cosine of x, tangent of x, cotangent of x, secant of x, cosecant of x. Am I missing anything? Have you guys talked about natural log of x yet? Okay, great. Good. Eventually natural log of x. That's kind of, and then I guess inverse trig functions eventually, maybe today. So the derivatives here are p times x to the p minus 1, e to the x, derivative of sine is cosine, derivative of cosine is negative sine. I do kind of like breaking up the trig derivatives into like pairs of cofunctions. Derivative of tangent is cosecant squared of x. Derivative of cotangent of x is negative cosecant squared of x. Derivative of secant of x is secant of x tangent of x. And derivative of cosecant of x is negative cosecant of x cotangent of x. And then the chain rule version of all of these is just replace x with stuff and multiply by the derivative of the stuff. Yeah. Sure. Yes. We can do. So in fact, yeah, we can talk about that in. Give me just a moment to talk about that. But yes, we can definitely talk about it in a second. So we have our chain rule versions over here. So instead of x to the p, we have some stuff to the p. And the derivative is p times your stuff to the p minus 1 times stuff prime. I like to write stuff, even though it's super annoying. a lot of people choose to use the letter u instead, but we're thinking of u as a function of x. So you can totally write it like this, or you could say instead of writing e to the stuff, you could say the derivative of e to the u is going to be e to the u times u prime, or e to the u times du dx. But they're really the same thing. U is just my stuff here. So I've got e to the stuff times the derivative of the stuff. If my function is sine of some stuff, so I am going to write u because it's just easier than writing stuff. The derivative sine of some stuff is cosine of the stuff times the derivative of the stuff. And you can write u prime or you can write du dx, whichever way you prefer. They mean the same thing. Yes. Okay, so our logarithm is going to be on your exam on Monday. Okay, yeah.
He showed us the equation, but then he didn't finish.
Okay. Well, we'll talk about logarithms when we talk about implicit because they kind of show up there.
Basically, what you do afterwards is that you have to know the derivative of natural log to solve an exponential equation like that.
Right.
He's taught us like.
Okay, well, we'll get there. I'll talk. There's a moment where I'll talk about logarithms for sure. So then the rest of these just follow the same kind of pattern. The derivative tangent of some stuff is secant squared of that stuff times the derivative of the stuff. The derivative cotangent of some stuff is negative cosecant squared of that stuff times the derivative of the stuff. And lastly, and kind of oddly, I think, the derivative secant of some stuff is secant of the stuff times tangent of the stuff. The stuff shows up twice times the derivative of the stuff. And similarly for the derivative cosecant of some stuff, the derivative is negative cosecant of your stuff times cotangent of your stuff times the derivative of your stuff. Okay. So it'd be lovely if we had more time, but we don't. So let's talk about implicit. Yeah, implicit. Yeah, implicit. Where'd you go, implicit? Sorry, one second. Cool. All right. So I had these notes somewhere. Apologies, I was looking for something. There we go. Cool. Implicit differentiation. So the thing to know about implicit differentiation is you're usually making the assumption that y is a function of x, even though you might not actually be able to solve for y as a function of x. A very common example to look at is this example, where we have the equation x squared plus y squared equal to 25. The equation of a circle, certainly not a function, right? If you draw this, you can totally see that it fails the vertical line test. That doesn't mean you can't find the slope of a tangent line, though. So one way you can find the slope of the tangent line, let's look at the point over here. Let's look at the point 4, -3. I would love to find the slope of the tangent line right there. So in this example, you could actually solve for y as a function of x. But it's kind of annoying because if I solve for y, you get y squared equal to 25 minus x squared. You take the square root of both sides, you get y equal to plus or minus the square root of 25 minus x squared. Or if you prefer, plus or minus 25 minus x squared to the 1/2 power. And then to be able to accurately take the derivative and find the slope of the tangent line, you have to know which piece of the function we're looking at. In this case, we're looking at the bottom half because we see that y is negative. So we know that we should actually be using y equal to the negative square root of 25 minus x squared. So now let's find the derivative. The derivative for this bottom half is going to be, well, the negative sign hangs out in front. We're going to use the chain rule. The derivative of some stuff to the 1/2 power is 1/2 times our stuff to the negative 1/2 power times the derivative of our inside stuff, which is negative 2x. I would probably simplify this. I would rewrite this as positive x over the square root of 25 minus x squared. The -2 and the -1/2 cancel, and the 25 minus x squared to the -1/2 becomes square root of 25 minus x squared in the denominator. Great, let's plug in x equal to 4 and see what we get. We plug in x equal to 4, dy dx evaluated at x equal to 4 is going to be 4 over the square root of 25 minus 16, which is 4/3. Which seems plausible, right? Certainly the slope I've drawn looks like you should have a positive slope. Two things. One, it's annoying to do that. Two, you usually can't do that. So most of the time, you won't actually be able to solve for y as a function of x. And when that's the case, you have to resort to other methods. So what we're going to do here is instead say, well, great. Even though it's not true, we're going to pretend that y is a function of x. And although I wouldn't usually write it as f of x, I'm going to here. So we're going to say, great, we have x squared plus f of x squared equal to 25. And all we're going to do is we're going to differentiate straight away. So we're going to take the derivative of both sides with respect to the variable x. Always with respect to x. So what's the derivative of x squared? What's the derivative of some stuff squared? 2 times my stuff to the first power times the derivative of the stuff. And then it's equal to what's the derivative of 25? Right. Be careful. For some reason, when people do this, they often tend to like leave the other side just as what it was. Make sure you take the derivative of the other side as well. So if it was a constant, the derivative should be 0. And now we're going to solve for the derivative because that's what we're trying to find. The derivative, aka the slope of the tangent line. So we're going to solve for f prime of x. So we're going to subtract 2x. We have 2 times f of x times f prime of x equal to -2x. And then we're going to divide by 2 f of x to get f prime of x equals -2x over 2 f of x. You can cancel the 2's if you want and say it's -x over f of x, or you could even say it's -x over y. Because f of x is equal to y. I just replaced it. And then if you plug in your point of tangency, 4, -3, so I will point out that f prime of x evaluated at 4, -3, I'm plugging in 4 for x and -3 for y, and I'm going to get -4 over -3, which is positive 4/3. The same number. And very conveniently, we didn't have to think about if we were using the top half or the bottom half. That was kind of taken care of for us by the fact that we knew we were plugging in y equal to -3. We automatically had to be using the bottom half because we were using a negative y value. So that's kind of the gist of implicit differentiation is we're going to make the assumption that y is a function of x, and then we're going to differentiate all the way, and then we're going to solve for y prime afterwards. And usually you're not going to write y equals f of x, you're just going to leave it as y. So normally we would have written this as just like 2x plus 2 times y prime equal to 0. Or if you prefer, 2 times y times dy dx. Either way is fine. Take some examples. So let's do the following. We want to find, dy dx for the equation x cubed plus y to the 4th plus tangent of y equal to e to the y plus sine of x. So when you look at this in your head, you should be saying y is my stuff, right? Y is my function of x. So when I have y to the 4th, it's not, the derivative isn't just 4y cubed. The derivative is 4y cubed times the derivative of my stuff, which is the derivative of y, which is y prime. So when I start differentiating both sides, the derivative of x cubed is just good old 3x squared because the variable where you're differentiating with respect to is x. But the derivative of some stuff to the 4th power is 4 times my stuff to the 3rd power times the derivative of my inside stuff. And that's why when I said the implicit differentiation is just a chain rule, that's what I mean. You're really just using the chain rule again, just in a kind of slightly different way of thinking about it, but it's still really the chain rule, where y is always your stuff. So whenever you have a function with a y in it, at the end of that, you always have to multiply by the derivative of y, either y prime or dy dx, whichever notation you prefer. Okay, this next one's slightly tricky, even though it doesn't seem like it should be. The derivative tangent of y is going to be secant squared of y times the derivative of the inside stuff. And here, it always feels like a silly question, but what's the derivative of y? It's the derivative of y, which is dy dx. So if you just have a y in there, you end up multiplying by dy dx. Or you could say it's 1 times dy dx if you prefer to think of the derivative of y as being 1 and then multiplying by dy dx after that. On the right-hand side, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of sine of x is cosine of x. And as far as this problem goes, that's the only part of it where we're actually using any calculus. After this, it's just algebra. We have to collect all our dy dx's on one side, factor out whatever is multiplied, factor it out, and then solve for dy dx. So here are my terms that have dy dx. Let's collect all those on the left, everything else on the right. So I'm going to have 4y cubed times dy dx plus secant squared of y times dy dx minus e to the y times dy dx equal to cosine of x minus 3x squared. And then we factor out the dy dx from the left. So we're left with dy dx times 4y cubed, that's a 3, believe it or not, plus secant squared of y minus e to the y is equal to cosine of x minus 3x squared. And then finally, solving for dy dx, we get dy dx equal to cosine of x minus 3x squared divided by 4y cubed plus secant squared of y minus e to the y. Kind of terrible, but it's always the same process. You're always doing the same 3 things. Differentiating both sides, collecting all your terms that have y prime or dy dx on one side, factoring it out, dividing by what's left over. Always the same steps. As long as they're asking you just to find the derivative. Yeah. Sure. So let's look at a slightly different problem. Well, same idea still. Do this here. So let's say we wanted to find the slope of the line tangent to the equation x cubed plus xy plus y squared equal to 3 at the point 1, 1. Okay. I'm going to show you, do I want to do this both ways? Not really, but it might. So I'm going to show you the easy way first. Start off as usual. Take the derivative of both sides. So differentiate both sides. Derivative of x cubed is 3x squared. The derivative of x times y, we're going to have to use the product rule. So it's going to be the derivative of x, which is 1. Leave y alone. Plus, switch it up. Leave x alone. Multiply by the derivative of y, which is the derivative of y prime, or dy dx. Either way is fine. Just pick one and use it. And then the derivative of y squared is going to be, well, the derivative of some stuff squared is 2 times your stuff to the first power multiplied by the derivative of your stuff. Equal to the derivative of 3, which is 0. Okay, after this first step, you could go 2 different ways. There's definitely a better way to go. So this only applies if you're asked to find the slope of the tangent line at a particular point, right? The previous problem just said, find the derivative. So we did. This problem didn't actually ask us to find dy dx or y prime. It just said find the slope of the tangent line. So one way you could do this is just by plugging in right away. That's totally valid. So I'm going to plug in 1 for x and 1 for y, and life's going to get a lot easier. I'm going to have 3 times 1 squared plus 1 times 1 plus 1 times y prime plus 2 times 1 times y prime equal to 0. That seems pretty great. 1y prime plus 2y prime is 3y prime. So I have 4 plus 3y prime equal to 0. 3y prime equals -4. Y prime equals -4/3. So my slope at the point 1, 1 is -4/3. And in my opinion, that is always the way you should do it when you're doing implicit and they ask you to find the slope at a particular point. Immediately after taking the derivative of both sides, that's when you plug in your point. You could go the other way. You could solve for y prime first. I think it's more work to do it that way. If I solve for y prime first, I'm going to have xy prime plus 2yy prime equal to -3x squared minus y. And then you're going to factor out a y prime. Right? It already feels like I'm doing way more work. And then divide by x plus 2y. And there's your derivative, which I guess you would want if they asked you to find the derivative, or they asked you to find the slope at multiple points, then you probably do it this way first. And then you can plug in and say, okay, great. Y prime evaluated at 1, 1 is going to be -3 minus 1 over 1 plus 2, which is also -4/3. So either way is fine. I just think you're going to save yourself some effort if you do it this easier way where you plug in immediately after differentiating both sides. You do have to take the derivative of both sides first before you plug in your point. Questions about that? This is implicit, yeah. So the way I typically identify if a question is an implicit differentiation question is if you see an equation with x's and y's kind of all mixed up together, and you can't just write y equals something with just x's in it. So to me, seeing this with the x's and y's all on the same side is very obviously implicit because you can't solve for y here. Ooh, yeah. Sorry, I just did something weird. Okay, so yeah, let's look at. No, we'll go that way first. One of the uses of implicit differentiation is it allows us to find some derivatives of some new functions. For example, if I wanted to find the derivative of the natural log of x, so here's what I would do. I'm going to write y equals natural log of x, which I don't know how to take the derivative of, but I'm going to rewrite this as an exponential equation. I can rewrite this as e to the y equals e to the natural log of x, or e to the y equals just x. And now we're going to do the implicit differentiation thing. We're going to take the derivative of both sides. What's the derivative of e to the x? Yes. What's the derivative of e to the stuff? Times. Right, times the derivative of the stuff. What's the derivative of x? Just 1. So then solving for y prime is equal to 1 over e to the y. Oh, that's disappointing. I really wish my answer didn't have y's in it. Because I would love to know what the derivative of the natural log of x is in terms of x. But luckily, we already know that e to the y is equal to x. So we can say, oh, great, my derivative of y prime here is just 1 over x. So it is the case that the derivative of the natural log of x is in fact equal to 1 over x. Cool. You can also use this to then find the derivatives of other bases. So like, for example, if you wanted to find the derivative of, say, 3 to the x. I have varying ideas about how you should do this, to be honest. Let me talk about both of them. So one way to do this that is not my favorite, but I've come to not hate it, is to rewrite this as the derivative of e to the natural log of 3 to the x. Totally valid. You can write anything as e to the natural log of that anything, and you haven't actually changed it. Because the e and the natural log undo each other. But then we can use rules of logarithms and say, great, this x gets to come down in front of the natural log of 3. So this is really equal to the derivative of e to the x times natural log of 3. And here's how I want you to think of this. This is the derivative of e to the stuff. Quick question on the side. What's the derivative of 7 times x? Cool. What's the derivative of x times 5? 5. Right? So I didn't really change anything. Order of multiplication does not matter, right? Whether it's x times 5 or 5 times x, it's still a constant times x. It's still a line whose slope is 5 all the time, even though I wrote it in a dumb way. Okay, one more thing. What's the derivative of x times pi? Sorry, you can't show me on your fingers because you don't have that many fingers. Well, I mean, I guess you could be like, no, okay. It's how many? It's pi. Or generally here, and there is a reason, don't worry, the derivative of x times the constant is the constant every single time. Okay, great. Keep that in mind. If I take the derivative of e to the stuff, it's going to equal e to the stuff times the derivative of the stuff. Oh, what's the derivative of x times natural log of 3? Natural log of 3, because the natural log of 3 is just a constant. Right? There aren't any variables there. And I really don't want to leave my answer looking like this because it's atypical. And we should know that e to the x times natural log of 3 is just the same as e to the natural log of 3 to the x, which is just the same as 3 to the x. So really, we should write our answer as 3 to the x times natural log of 3. And more generally, the derivative of any base raised to the x power is that same thing, b to the x times the natural log of b. You could also do this using implicit differentiation, but it requires knowing that the derivative of the natural log of x is 1 over x. Let's do it though, because it's kind of interesting. And not just interesting, it's worthwhile. So let's say we want to find the derivative of 6 to the x using implicit. And here's what I'm going to point out. We already know what the answer should be. The answer should be 6 to the x times natural log of 6. But using implicit, we have to have an equation. So we're going to start with y equals 6 to the x. And then what we're going to do here is we're going to take the natural log of both sides. Because the idea here is like we're kind of pretending like we don't know how to take this derivative. So we say that the natural log of y equals the natural log of 6 to the x. And again, the reason for taking the natural log of both sides generally is so that you can get that variable out of the exponent. Then we're going to say, okay, great. Then the natural log of y is equal to x times the natural log of 6. And now we can take the derivative of both sides. Okay, I know we just talked about it, but what's the derivative of the natural log of x? 1 over x. So in the same sort of way that all of our other chain rule things have worked, if the derivative of the natural log of x is 1 over x, then the derivative of the natural log of some stuff should be 1 over the stuff times, I said the magic word. What do you have to multiply by? The derivative of the stuff, right? That's why we want to always keep that chain rule thing in mind, right? If your thing isn't just x, if it's some stuff, at the end of the process, you have to multiply by the derivative of the stuff every single time. So I took the derivative of the natural log of some stuff. I got 1 over the stuff, and I have to multiply by the derivative of the stuff. The right-hand side is much easier. You have x times the constant. The derivative of x times the constant is just the constant. Now we solve for the derivative, because that's what we're trying to find, the derivative of y. So dy dx is equal to y times natural log of 6, just multiplying both sides by y. And then we're going to replace y with what we know y is equal to. So our derivative here is equal to 6 to the x times natural log of 6, exactly as we thought it was going to be. So that's how you do this thing implicitly. But again, it requires the knowledge of the derivative of the natural log of x to start off with, so. keep it. Really, you should probably just memorize the fact. So I guess you could say, adding to our list of derivatives, we have, right, if your function is b to the x, the derivative is b to the x times natural log of b. And if your function is more complicated, which I know we haven't seen an example of this, but I'm gonna say it anyway. If your function is b to the stuff, your derivative is going to be b to the stuff times natural log of b. And then you have to multiply by the what? The derivative of the stuff prime. Exactly. So for example, let's just throw in an example over here. If I was going to take the derivative of 4 to the x cubed plus 1, well, I have 4 to the stuff. The derivative is going to be 4 to the stuff times the natural log of 4 times the derivative of the stuff, which is 3x squared. And I didn't put parentheses around 3x squared because it's only one term, but it would be totally safe to put parentheses around it if you wanted to. Why don't you all try finding the derivative of, do I want to make it challenging? Yes, I kind of do. Yeah, sure. 5 to the x squared times sine of x. Ooh. I did say x squared times sine of x. So when you take the derivative of the stuff, what rule are you going to have to use? The product rule. Yes, I can. That. Yeah, okay, cool. Love to give you more time, but you have so little of it. Let's go ahead and see what we get here. Same pattern. Derivative of 5 to the x is 5 to the x times natural log of 5. The derivative of 5 to the stuff is 5 to the stuff times natural log of 5 times the derivative of the stuff. So it's going to be 5 to the stuff times natural log of 5 times the derivative of the stuff, which is the product rule. So it's going to be the derivative of x squared times sine of x plus x squared times the derivative sine, which is cosine. And sorry, I'm squeezing that in there. I know it's terrible. That's it. I will say, because I've seen it so many times, whenever you're differentiating an exponential function, like 3 to the something, or e to the something, or 5 to the something, that original expression always shows up exactly as is. Every time. So whenever you differentiate some exponential function, you always get that exact exponential function and then multiply by some other stuff, like the natural log of the base and the derivative of the exponent. Cool. One more implicit thing, because you guys mentioned it. We also do this kind of thing for finding the derivative of the inverse trig functions. So for example, the one I know you're supposed to have learned at some point in this class is the derivative of the arc tangent of x. So here's how we're going to do this. So we don't have a ton of time, but I'll just find out arc tangent of x is the function that's, or the inverse tangent of x is the function that's undoing the tangent function. So I know over here, the tangent of pi over 4 is equal to 1. And tangent of pi over 3 is equal to root 3. What that means is the arc tangent of 1 is equal to pi over 4. Or as I like to say, the angle whose tangent is equal to 1 is pi over 4. Or the angle whose tangent is equal to root 3 is pi over 3. Just like any other inverse function, you're literally interchanging the role of the input and the output of x and y. So the reason I write this is because if I said that the arc tangent of x was equal to y, that would be equivalent to saying the tangent of y was equal to x. Because thing the arctangent is equal to is an angle. And the thing you take tangent of is an angle. So those should kind of match up. Great. Here's what we're going to do. We're going to start off by saying y equals the arctangent of x, and then taking the tangent of both sides, or rewriting it as tangent of y equal to x. Most of these inverse trig function derivatives kind of start off this way. And then we're going to take the derivative of both sides. And just like every other time I've said this, the derivative tangent of x is secant squared of x. The derivative tangent of some stuff is going to be secant squared of that stuff multiplied by the derivative of the stuff. On the other side, much easier, the derivative of x is just 1. And just like the other ones, we're going to solve for the derivative. So the derivative dy dx is equal to 1 divided by secant squared of y. This one's a little trickier in that to get back to x, you need to either use a trig identity or you need to use a triangle. I prefer a triangle, so I'll just point out tangent of y equals x means that over here, tangent of y, I'm going to rewrite that as equal to x over 1. But in right triangle trigonometry, we know that tangent is equal to which side over which side? Let's see, SOHCAHTOA. Tangent is the opposite over the adjacent. So if we draw ourselves a little right triangle here, where the angle is y, then tangent of y should be the opposite over the adjacent. We can use the Pythagorean theorem to find the third side. So this third side is going to be 1 squared plus x squared equals question mark squared. So the question mark is equal to the square root of 1 squared, which is 1 plus x squared. And then if we want to find secant squared of y, well, secant of y is the reciprocal of cosine. Cosine is adjacent over hypotenuse. The secant is hypotenuse over adjacent. So the secant is just the square root of 1 plus x squared over 1. And if we square that, look what we get. We get dy dx equal to 1 over secant squared, which is just 1 over 1 plus x squared. So it is indeed true that the derivative of the arctangent of x is equal to 1 over 1 plus x squared, or 1 over x squared plus 1, whichever way you like to write it. And just like anything you learn the derivative of, there's automatically a chain rule version of it. So if you know that the derivative of arctangent, sorry, you can't see that, apologies. If you know that the derivative of the arctangent of x is 1 over 1 plus x squared, then you also know that the derivative of arctangent of some stuff is 1 over 1 plus stuff squared times the derivative of the stuff every time. So it is indeed true that the derivative of the arctangent of x cubed plus 5x plus 7 is going to be exactly 1 over 1 plus your stuff squared multiplied by the derivative of the stuff. Yeah.
Could you remind us where the inverse trigonometric functions exist? Because I know there's like the control they exist when we apply math to them.
When you say like you talk about like a domain,
Yeah.
yes, but I guess I could, but I'd rather spend the last 20 minutes talking about some related rates questions because I think that's a little bit more necessary. So I'm happy to talk about that next week. I just don't think I should spend our time right now doing that. So, yeah, related rates. I know there's so much. Related rates. Also the chain rule, really, to be perfectly honest. I think I'm out of water. So let's look at an example. Yeah, let's just start with this example. So the idea with related rates is essentially you're going to have one thing changing at some rate and be asked to find how a related thing is also changing at some other rate. A very common first example is something like this. The radius of a circle is increasing at a rate of 2 inches per second. When the circle has a 5-inch radius, how fast is the area changing? Okay, there's a couple steps. There's like 4 or 5 steps I usually recommend for a related rates problem. The first step sometimes is drawing a picture. I don't think it's super necessary here because we know what a circle looks like, but we can still draw a picture and think of, okay, we got a circle and we know that the radius is getting bigger. The actual first step, so something they call this like the 0th step. The real first step is to ask yourself, what do I know is changing and what are they asking me to find is changing? So I know that the radius is increasing at a rate of 2 inches per second. So I know that the radius is changing. So the radius is increasing, which means I'm going to write down dr dt, the rate of change of the radius with respect to time, is equal to 2 inches per second. I usually don't care about including the units, but it's not wrong to include the units here. And then I also want to write down the thing they're asking me to find. Oh, they're asking me to find how the area is changing. So what I want to do is I want to find what dA dt is equal to. That's the goal of this problem. Okay. After we identify the things that are changing, I should say specifically the non-time things that are changing. So any non-time variable, in this case, area and radius, I want to find an equation that relates those variables. Usually it's some sort of geometry thing, like the area of a circle, or the surface area of a sphere, or the volume of a cone, or right, whatever volume or area thing, or circumference or surface area might be in play. In this case, it's the typical area of a circle. So relate the non-time variables. I should also mention, not every related rates problem is happening as time increases, but almost all of them are. Like occasionally there's ones where like pressure and volume are related by like if you go higher in elevation. So you ask like, how is the pressure changing as the volume as you increase elevation, and then you do that kind of thing. But most of the time it's how things are changing as time is changing. So relate the non-time variables. In this case, it's area equals pi r squared. And although I wouldn't usually write this, I will point out we are making the implicit assumption that area and radius are functions of time. We're not writing that down, although you totally could write it as area as a function of time equals pi times radius as a function of time squared. Although you don't usually do that. Okay, here's probably the hardest step for people to wrap their minds around. We're going to differentiate both sides with respect to time, or whatever the independent variable is. Great. What's the derivative of area? It's the derivative of area. It's dA dt. The derivative of pi r squared, well, I've got pi times some stuff squared, and the derivative of pi times some stuff squared is pi times 2 times my stuff to the first power times the derivative of the stuff. Oh yeah, implicit differentiation, right? Everything here is implicitly a function of time. And so when you differentiate, you're implicitly differentiating with respect to time, and you have to multiply by the derivative of the inside stuff. Also, if you're given this rate of change and asked to find this rate of change, both of those things better show up after you differentiate both sides so that you can actually find the thing they're asking you to find. So if these things aren't showing up and you know one of them, and you need to do the other one, they better show up. Otherwise, you got problems. After this, it's pretty straightforward. You plug in the things you know, you solve the thing you want to know. So step 4, plug in and solve. So we know that dr dt is 2. We know that r is 5. And so we can say that dA dt is equal to pi, I should say 2 pi times 5 inches times 2 inches per second. I'm not writing the units, but I am noting them because I'm saying, oh, I have inches, times inches per second, that's going to give me inches squared per second, which makes sense if I'm asking how an area is changing as time increases. So here I'm going to have 2 times 5 times 2 is 20 pi inches squared per second. Notably, if the radius had been larger, like if the radius was 10 instead of 5, the rate of change of the area wouldn't be the same. Right? The rate of change of the area would be 2 pi times 10 times 2, which would be 40 pi inches squared per second. So, and that makes sense, right? If the circle is bigger and the radius is still increasing at the same rate, then if you increase by some certain amount, you're going to get much more circle because you're adding on a whole lot more circumference worth of area. Okay, we got time for at least one more. Unless, I should say, are there questions about this before we do another one? Keep trying to drink water like this water is not going to magically appear. Okay, so yeah, let's look at this one. This one's a good one. So I'm going to say words, but I'm going to write down the pertinent things. So here are the words. Gabriella is standing 6 feet from her little sister Mia. Those are the names of Grant's children, by the way. So here we have Mia standing over here, Gabriella standing over here, and they're 6 feet from each other. Mia is holding a balloon. Mia accidentally releases the balloon and starts rising at a constant rate of 2 feet per second. So we've got a balloon and it's going up at a rate of 2 feet per second. So I'm going to label this here as H for height, or Y for height, or some variable name because that thing is changing. So whatever things are changing should get variable names. Whatever things aren't changing, like Gabrielle and Mia aren't walking closer to each other, I should just put in the number that represents how far apart they are. And then we're asked to find, so let's see, starts right. Oh, so I'm also going to write down over here. So here's my step 0 drawing the picture. Step 1, the height is changing at a rate of 2 feet per second. So dH dt is equal to 2 feet per second. After 4 seconds have passed, how fast is the distance between Gabriella and the balloon changing? So I want to know how fast that distance, which is also changing, is increasing or decreasing. It's increasing though. I'm going to call this, I like to call this S typically. Usually for diagonal lengths, I call them S instead. I don't use D because writing dt just looks weird. So we want to know what ds dt is equal to. And specifically, what is ds dt 4 seconds after the balloon was released? I also think when you're doing a problem like this and you're reading the question, it's worth it to kind of focus in on what's important and write that down as you go along. Okay, so we've got our picture. We know that H is changing at 2 feet per second. We know that we want to know how S is changing at the moment 4 seconds after release. So now that we've seen what's changing, we need an equation relating the non-time variables. I'm thinking, got a right triangle there, probably some Pythagorean theorem stuff. Typically, if you've got a triangle, it's either Pythagorean theorem or similar triangles. Like if you have a cone kind of thing, similar triangles show up. So here we're going to say, great, my equation is going to be 6 squared plus h squared equals s squared. And there's no reason to solve for anything here. Immediately after writing down the equation, differentiate both sides. Okay, what's the derivative of 6 squared? 0. Right, 6 squared is a constant. Don't get tricked. So 6 squared is derivative of 0. Derivative of h squared is going to be 2h times the derivative of h. Similarly, the derivative of s squared is going to be 2s times the derivative of s. You could cancel the 2's on both sides. That's not really important. And then finally, plug in what you know. So we should be able to plug in for everything except for the one thing we're trying to find. So should be able to plug in for h. Well, yeah, if we're try and find out what all this is equal to 4 seconds after release, and the height is increasing at 2 feet per second. How high are we? Yes. So the balloon is rising at 2 feet per second, and we've let this go on for 4 seconds. So it's 8 feet high. So we have h equal to 8 feet high. We know that dh dt is 2 feet per second. And we also better be able to figure out what s is. And we can, because we know that 6 squared plus 8 squared will equal s squared. Right. Now I'll point out most of the time in these Pythagorean kind of problems, they're usually, not always, they're usually going to give you nice numbers. So you should remember, or you should know, or be aware of the fact that there's a thing called a 3, 4, 5 Pythagorean triple. And the other two that sometimes come up are a 5, 12, 13. And if someone's really feeling themselves, 8, 15, 17. Now you might notice that none of these are the ones I said, right? We don't have a 5, 8, sorry, a 8, 15, 17, or a 5, 12, 13, or a 3, 4, 5. We have a 6, 8, but 6 and 8 are both 2 times 3 and 4. So really we have a scalar multiple of a 3, 4, 5. We have a 6, 8, 10. Or you could just use the Pythagorean theorem. You can say, great, yeah, 6 squared plus 8 squared equals s squared. 36 plus 64 is 100. 100 equals s squared. S equals 10. Yeah. That's right. There we go.
Well, we don't use the foundation.
For the s,
We don't plug back in the 85.
well, we're about to. We're about to plug in. I was just finding the values before I plugged them in. So these are the things we have. And then we're going to plug those into this equation here. So we're going to have 2 times 8 feet times dh dt, which is 2 feet per second, equals 2 times s, which you just found s to be 10, times ds dt. Right? There's our h, there's our dh dt, there's our s. And now we can solve for ds dt. So we have 2 times 8 times 2, which is 32, divided by 2 times 10, which is 20, equals ds dt. And then we can reduce that fraction. So ds dt is going to equal 8 over 5 feet per second. Or if you like decimals, 1.6 feet per second. Not surprisingly, slower than the balloon is actually rising, right? Because if it's rising at a rate of 2 feet per second, and you're asking how this distance is changing over here, it can't be any faster than that 2 feet per second, because that's kind of the fastest it's moving away from this point directly below it. Okay. There's no water there, James. No water. Yeah, let's get one more. Yeah, we can squeeze in one more example here. Yeah, we should do one like that. Okay, so. Yes. Sure. So exponential growth in decay. Yeah, so I imagine that's something, I mean, here's the kind of example I'm thinking of. I'm wondering if I'm just curious if there's something on this practice problem thing here that we can look at and just. No, I don't change. Okay, that's fine. So, anyway. Yeah, I really, okay. So I would imagine something like a 15-gram sample of an unknown radioactive isotope. Decays to 10 grams over 6 days. how long does it take for the original 15-gram sample to decay to 5 grams? That kind of thing? Does it seem like what you're looking for? Okay. So for exponential growth decay problems like this, I usually recommend setting it up. I like to use a table, meaning I want to make a table of times versus amounts. And also, I guess I should point out, we definitely need to know that the model for exponential growth or decay looks like y equals c e to the kt. So in the beginning, there were 15 grams. 6 days later, there were 10 grams. And I want to know how many days does it take to get to 5 grams? And I'll point out that the answer is not 12 days. Right? It's not a linear relationship. Right? You can't say that every 6 days it decreases by 5 grams. That's not what's happening. You could say every 6 days it's going to have 2/3 as much as it had before. So the thing is, these exponential relationships, the multiplication factor is actually what's constant over a certain amount of time. So I'm just going to point out that I know that at day 12, since it's 15 times 2/3 gave me 10, 10 times 2/3, which would be 20/3 or 6.66 forever. That's how much you'd have after 12 days. If you had another 6 days, you multiply by another 2/3. So just something to be aware of, that for exponential growth or decay, it's the multiplication factor over a set period of time that is constant. That's why we talk about a half-life. And a half-life is the amount of time it takes to multiply what you have by 1/2. Or the doubling time is a constant amount of time it takes to double the amount of cells you have. So it's the multiplication factor that's constant. So don't get tricked by something like this. This question was definitely written with the intent to trick you. Where I was like, oh yeah, if I do 0 to 6, 15 to 10, if they think 10 to 5 will be another same period of time, that's not the right answer. On the other hand, no, I won't say on the other hand because I only have so much time. So here's how you do this. I point out, well, to me, this doesn't feel like it's really a calculus question in that you're not using any differentiation skills, right? It's more of a pre-calculus, but still not important, just good to be aware of what we're doing. So here you'd first find C by setting y equal to 15, t equal to 0. And that's going to give you 15 equal to C. C is always your initial amount at time 0. And then we're going to plug in this next data point. I know that looks like it says log. That's 10 grams, not log. Then we're going to plug in 10 for Y. We're going to use 15 for C. And we're going to have e to the k times 6. And then we're going to solve for k. Divide both sides by 15, you get 2/3 equal to e to the 6k. Take the natural log of both sides. Natural log of 2/3 equals 6k. Divide both sides by 6, so 1/6 natural log of 2/3 is equal to k. Then our full model is y equals 15 e to the 1/6 natural log of 2/3 times t. And then to answer the question that was asked, we're going to plug in 5 grams for y and solve for t. So then and really solving for t is almost exactly the same process as solving for k. You divide both sides by your constant, so you have 5 over 15, which is 1/3, equal to e to the 1/6 natural log of 2/3 t. You take the natural log of both sides, you get natural log of 1/3 equals, pay attention here for a second, the natural log of e to all this stuff is just all that stuff. Finally, multiply both sides by 6. Divide both sides by natural log of 2/3. And that is your final answer without the calculator. It's definitely not equal to 12. I would love to say more, but it's 11:52, so I shouldn't.